In this video, we'll start to look at decision trees. Decision trees. And we'll focus on the CART approach to decision trees as introduced by Bryman et al. And it turns out, so decision trees are an extraordinarily conceptually simple approach to classification and regression. But it turns out that despite their simplicity, decision trees can be extremely powerful, especially when coupled with some randomization techniques that we'll talk about a little later on. They can give essentially the best performance of any current algorithms. Very surprising. So remember the basic setup, as always in supervised learning, is we have some data, and we're given a new point x or a bunch of new points, and we have to associate a y with the new x or x's. So the main idea behind decision trees, at least in this formulation, the CART formulation, is you form a binary tree and you minimize the error in each leaf of the tree. So that's the main idea. I will explain what that means through an example. So let's say these x's are in R2, something nice and simple that we can draw. So we've got our nice R2 here, and let's draw some points. Let's say maybe we've got some ones here, some red ones, and maybe we've got some ones down here, something like this, and maybe some ones here, something like that. And then we've also got, of course, another class. Maybe this one's got some zeros, some points which are labeled 0, something like this. Maybe something like that. Now, we have our data set. These are all points, and each of them has a label. And in a decision tree, you choose a sequence of binary splits of the data. So first, let's say, if you want to split this data in some good way, maybe a first choice would be, let's split on the first coordinate here. So let's split on this coordinate. That would be a good choice because we can separate all these ones over here from everything else. And then maybe for the next split, so now we have two regions. So this divides R2 into two disjoint regions. And now we consider each of these regions. This one looks excellent. Everything's the same. But over here we need to do some more splitting, perhaps. So let's choose this one, say. Maybe we choose split. Now we separate this into two regions again, and maybe we're going to split something like this, and then maybe we'll split here or something. Maybe we'll split that one also. So this gives us some nice separate regions, and this defines a tree, a binary tree. So what's the binary tree associated with this? That sequence of splits. So first, if we call this axis here, let's call it the xi1 axis, and we'll call this the xi2 axis. So it's just the first coordinate in each of these x's, and this is just the second coordinate. So the first split I drew, let's say maybe this is, I don't know, maybe this is at 1 or something. Maybe that happens to be the point 1. Maybe this happens to be 2. Maybe this is, I don't know, Maybe this one's like 1.8 or something. Maybe this is 1. So the first split says, is xi1, this coordinate, is it greater than 1? And if it is, if it's yes, so if yes, we go that direction, and if no, we go this direction. So no, all these points are no's, so they all go down this path in the tree. And now, let's go ahead and take care of this. So this now, since we haven't split this anymore, this becomes a leaf in the tree. And let's draw the leaves according to the number of points of each class. So how many zeros? So we get 0 zeros. So let's put 0 for 0 zeros, and we get 4 ones. Now on this side, on the right side, when all the points that were greater, we then split along this, along the 2 axis. We made this split. So the next one is xi2 greater than 1? And if yes, so yes, we're going to go that way. No, we're going to go this way. So if it's yes, right, so if it's greater, we're up here, and we have to split one more time. So is xi1 greater than 1.8? That was that one. We get yes and no. So the yes, right, so when it was greater, then that leaves these. So this would be 1 0 and 4 ones. Right, so greater and greater. And on this side, we get another leaf. That would be this one. So we get 4 zeros and 0 ones. Now we had to split this guy again. So we're going to split this along xi1 greater than 2. And we get 2 more leaves. So we get whatever this is. So let's see. Greater than was this one. So that's 3 zeros, 0 ones. And this one, of course, is just, whatever, 2 zeros, 3 ones. So this is a decision tree. And, well, I have to say, how are we going to classify the points? So this defines a tree. And what we will do, so we have our binary tree, and now we want to minimize the error in each leaf. And in particular, I should say the training error. That says training. So it's the error on our training data. And on our training data, to minimize the error at each leaf, so let's just say that was no, that was yes, that was no. Okay, so to minimize the error at each leaf, we would just take, in this case, since this is classification, we would just take a majority vote. So any new point we get that falls down this path that ends up at this leaf, we would classify as a 1. So let's see. So if we got a point here, so let me draw a new point. Let me pick a more interesting one. Let's see. So say we get a new point here, something like that. So this new point, so they say this is our x. So this is x. So we come down here, we say, okay, it's greater than 1. So the first split tells us to go down this path. So we go down here. Now, is xi2 greater than 1? And no, it's not, right? So we go down here. Now we're at this node, and we say, is xi1 greater than 2? And yes, it is. So we're down here, and we classify this according to the majority vote, which says make it a 0. So that would be classified as a 0, a new test point. And if we got a point here, we would do the majority vote again. So maybe this point here, we would say it's a 1, and so on. So you get the idea. So the classes that we predict, so the function that we predict, so we constructed, so this this defines a function from x's, from points x in R2 to y's, that's constant on each of these regions.